Um, so yeah, hi to you all. Thank you very much for coming, and welcome to the first of the Algebra representation theory for this term. And this week, Alok Paran from the Open University of Israel will be speaking on the Nullstellensatz. Very appreciate, very friendly to open some up. So take it away, Alok.
So thank you all very much for inviting me to speak at your nice seminar. And special thanks to Adam, who was very helpful setting everything up. Okay, so I'd like to start this talk with some working. Maybe I need to do something.
Yeah, just based up or down.
Very well.
Just
Yeah.
yeah, that's good.
Okay, so I'd like to start with some classical 19th century motivation. Consider the ring of polynomials in n variables over the complex numbers, and let J be an ideal in this ring. Well, then we can associate to this ideal the zero locus, the set of common zeros of all polynomials of J in the affine space C to the n. Conversely, given a set of points in C to the n, we can associate the ideal of vanishing, all polynomials vanishing at all of these points. So on the one hand, we have these algebraic objects, these ideals. On the other hand, we have these geometric objects, these sets of points. And the most basic fundamental question of algebraic geometry is what happens if you try to go back and forth between algebra and geometry? So what is I of Z of J? And the answer, of course, is the celebrated Hilbert's Nullstellensatz, which tells us that I of Z of J is simply the radical of J, which we can define explicitly as a set of roots of elements in F, of elements in J, or implicitly as the intersection of prime ideals containing J. And this is sometimes called the strong version of the Nullstellensatz. There is also the so-called weak version, stating that if J is a proper ideal in this ring, then there is a common zero to all elements of J. And the terminology weak and strong is somewhat misleading because it is, in fact, it's very easy to see that the weak version is a consequence of the strong version, but there is also a famous trick which we'll mention later to deduce the strong version from the weak version. So this is just one result, the Nullstellensatz. Now notice that in the special case where you have only one variable, well, what is then a proper ideal? It's just an ideal generated by one polynomial of positive degree. So in this case, the statement is simply that this single polynomial has a zero, which is the fundamental theorem of algebra. So one way to think about the Nullstellensatz is as a higher dimensional generalization of the classical fundamental theorem of algebra. Okay, so all of this I'm sure everybody knows. Now let's jump to something maybe slightly less well known. Now let's consider the quaternion algebra, the classical Hamilton quaternion algebra with the classical multiplication rule. Everybody kind of learns that as an undergraduate. And then we have the following theorem from 1941, stating that every non-constant polynomial with the coefficients written to the left of the variables, the coefficients here are quaternions, has a zero, which is a quaternion. In other words, we have a fundamental theorem of algebra for the quaternions. And this was proven by Niven for odd degrees and by Jacobson, Nathan Jacobson, that everybody knows from the books. He was very young at the time. That was one of his first results. Niven and Jacobson proved, Niven proved the odd case, Jacobson proved the general case. Okay, so I guess you can see where I'm going with this. If the Nullstellensatz is a higher dimensional fundamental theorem of algebra, and we do have a fundamental theorem of algebra for the quaternion, we also have a higher dimensional version of that? Can you extend this result of Jacobson to higher dimensions? And this is the motivational question for this talk. So I was randomly thinking about this a few years ago, and I told my colleague Gil about this question, and he was interested too. And then we said, okay, everything involved in this question, all of the notions, are completely classic. So you could have asked this question in 1941. So maybe people were somewhat preoccupied at that particular point in time. But you could have asked this question. And so we had expected to find the answer in the literature. So we started to search. And to our surprise, we could not find an answer. We did find some related results, one of which I will mention later, but we did not find a proper answer. And so we said, okay, let's try to figure it out for ourselves. Probably you can just do it like the complex Nullstellensatz, so it should be a fun exercise. Let's see what happens. Things turned out to be more interesting than that. So first, we need to properly formalize the problem. So consider the ring of polynomials in a central variable over the quaternion. So a central variable simply means that you use the usual product rule, just the same one you write with commutative polynomials. A different way to say it is that you look at the ring where the source of non-commutativity only comes from the coefficients for the quaternions, and the variable does not. The variable is somehow almost commutative. So it's a very natural generalization of the usual ring, and it's standard fact to know that this is a left and right principal ideal domain. So if you have a left ideal in this ring, it is generated as a left ideal by a single polynomial. Now let's talk about substitution in such polynomials. So if you have a polynomial in this ring and you have some quaternion, you can just plug it in. And once you plug it in, you get some quaternion. But now you need to be a bit careful and note that substitution is generally not a homomorphism, it's only a half homomorphism. By a half homomorphism, I mean that the kernel of this map is only a left ideal and not a two-sided ideal. So if you have a polynomial vanishing at, say, some quaternion z, then so is every left multiple of this polynomial, but the other way around is not true, because generally speaking, fg of z is not the same as the product fc times gz. Nevertheless, you have the following kind of nice substitution formula that fg of z is f of z conjugated by g of z times g of z. So not all is lost. Similarly, we can consider the ring of polynomials in n central variables. So again, just the usual product rule, the variables commute with everything. Non-commutativity only comes from the constants. But now you have a problem. Consider the polynomial xy. Since our variables are central, this is the same as the polynomial yx. What happens if you try to plug in I and j? Well, if you write it like this, you should get I times j, which is k. But if you write it like this, y times x, then you get ji, which is minus k. So it's not, you can clearly see that this is not well defined. Another way to see this problem is to note that if you have 2 points that do not commute, then the left ideal, the so-called innocent left ideal, x minus a, y minus b, is not actually a proper ideal. You can check that in this case, it's the whole ring. On the other side, if you do have a pair of points that commute, pair of coordinates that commute, then substitution is well defined, and the value of the substitution is the unique element such that f minus this element belongs to this ideal, which now is a proper left ideal. This leads me to the following definition. We will call this quaternionic central affine space, which is simply all points where all of the coordinates commute. So for example, j plus k minus j plus k is a point, but I and j is not. And as we have just seen, I should mention that it immediately follows that if you have a point in the space where everything commutes with everything, then if you look at the field generated by the coordinates, then you get some copy of the complex numbers. If it's not all real, inside the quaternion. So topologically speaking, you can think of the space of the central applied space as consisting of uncountably many copies of C to the n all intersecting at R to the n. That's the geometric picture. And this is exactly the space of points where substitution is well defined. You cannot substitute anywhere else. Yeah, and it immediately follows that if you look at the left ideal, if you look at a point in the space, you look at the left ideal generated by x1 minus a1 and so on, this is precisely the kernel of the substitution map at this point in the space. Okay, now there are many papers in the literature dealing with properties of two-sided ideals in such polynomial rings in central variables, but as we saw, we have to also consider one-sided ideals, otherwise we are missing out on a lot of the geometry. There are actually not that many papers studying properties of one-sided ideals. However, there is this paper, it's from 1978 by Amitsu and Small. Amitsu, for people unfamiliar, was one of the big names in non-commutative ring theory in the second part of the 20th century. And in this paper, they studied this ring, and the main result is the following. Take a division ring, so it could be the quaternions, but any division ring, and take a maximal left ideal in this ring. Then if you look at the quotient module of this ideal, it is finite as a left D module. And they call this result a Nullstellensatz over division ring. Though I think that a better name would have been Zariski's lemma over division rings. And in the commutative case, the Nullstellensatz is an immediate consequence of Zariski's lemma. Anybody who studied algebraic geometry studied this in the first week. But here, this is not the case. So maybe the terminology is a bit misleading. We'll return to this paper a bit later, but we are interested in the specific case where our division ring is Hamilton's quaternion, and in this case we can say much more. So first we have the weak central Nullstellensatz, that's how we call it. Take a proper ideal in this ring. There exists a common zero in the central affine space for all polynomials in this ideal, a proper left ideal. More precisely, if you look at the maximal left ideals in this ring, they are precisely those of the form corresponding to points in the central affine space. So this looks exactly like the classical weak Nullstellensatz, only you have to work with the central affine space, and you simply have no choice because everywhere else substitution is not well defined. And in the case of one variable, this reduces exactly to the Jacobson theorem from 1941 mentioned before. Okay, so we have the weak form of the Nullstellensatz. No, we prove it by some other means, and the proof of this is not difficult. This is a rather straightforward result, a two-page technical proof, nothing special. What about the strong form? This is where things get interesting. So let's take a left ideal in this ring, and let's look at the set of points, z of j, the set of common zeros of all polynomials in this ideal. And conversely, given a set of points in the central affine space, we can look at the left ideals of polynomials vanishing at this point. And of course, you can ask, what is I of z of j? What happens if you try to go back and forth between algebra and geometry? Okay, so what would you guess? Well, the first guess is the same answer as in the complex case, right? That this should be a set of roots of element in J, the radical. So we tried to prove this, and we said, okay, let's see how to prove it in the commutative case. So I'm sure many of you have seen this in the famous Rabinovich trick. I can do it in one slide, how to prove it in the complex case, the strong version. Just in one slide, you take an ideal, and you take a polynomial vanishing at the zeros of this ideal, say non-zero, and then you extend one dimension higher. You look at the ideal J prime generated by all elements in J, and 1 minus yf, where y is some extra variable that you introduce into the problem. Now, clearly, if you have a common zero for all elements in J, then by our assumption on F, F will vanish there, and so 1 minus YF will not vanish there. So you simply have no common zero to all elements in J prime, and hence by the weak Nullstellensatz, J prime is the whole ring. Which means that you can find some coefficients such that you get this equality, you get 1, and now you simply plug in y goes to F inverse, so that the first term disappears, and then you get this equation where the coefficients are now rational functions involving only F in the denominator. And then if you simply multiply by some large enough power of F, then on the right hand side you get F to the n, and in the left hand side you get coefficients that are polynomials, and this hi are the ideal J, which means that F belongs to the radical. So that's how you prove the Nullstellensatz from the weak version in the commutative case. And we said, okay, let's try to do the same. So you can do this the first step. You can extend one dimension higher, but then you cannot come back down. And the point is that substitution is not a homomorphism. So you cannot simply say, oh, let's plug in y goes to F inverse and translate the information back down to the ring with you started with. It just doesn't work. So there's a problem. Okay, now you can say, well, is this just a technical problem? No. We simply have a counterexample, even in dimension 1. So take this polynomial x minus I, x minus j. It might not be obvious, but it only has a single zero, namely j. I is not a zero, you can just plug in a j. You seem surprised. Yeah. Well, let me just say it, because so what is this polynomial, right? You have x minus I. So it's right? Now what happens if I plug in I? You get minus 1 minus I plus j. So it's 1 minus I minus I plus j I plus. So there's a minus number, right? Yeah, it's minus here, right? It's minus here. So it's minus k, so it's plus k, so you get 2k. So you don't get 0. Okay. So you can see the problem.
So valuation is not well defined.
No, this is in one variable. Here the valuation is defined everywhere because there's only one coordinate to plug in. So you can plug in any quaternion.
It depends on the represents.
No, you can plug in any quaternion you like in this polynomial. The point is that the surprising point is that if you plug in I, you don't get 0. If you plug in j, you do get 0.
Right. So it depends on the represents. Values you replace every x with an I.
You place.
Okay, maybe I'm.
No, I just write down. So what happens is I think I see the point. So first you have to open up the polynomial and write it in this standard form. This is how we define substitution, and then you just plug it in everywhere instead of x, and then everything is defined.
So are you also okay? Are you also doing that for higher end? So like when you evaluate the central line, the central line space here is just h.
Exactly.
So to evaluate, you still need to write the standard form for you evaluate.
So if you're right, but if you have a point in the central affine space, then it doesn't matter how you write. If you have more than one variable, then it doesn't matter in which order you write the variables, as long as you write the coefficients to the left of the variable.
So we need to do that.
Yeah. Well, very good question. Okay, so we have this polynomial. it has only the 0j, which means that the polynomial x minus j vanishes at all the zeros of f. But you can just simply directly check that no power of x minus j belongs to f. So I of z of j is not what you would expect. Okay, well, if it's not what you'd expect, then what is it, right? That's the question. You should have some description. So we thought about it for quite some time, and we had some guesses which we could not prove. And then we found, accidentally, something very useful. We found a PhD thesis of Manuel Reyes, who was at the time a student of Lamb in Berkeley. Lamb is a big name in non-commutative ring theory. And his thesis is dedicated to the following question: how should you define a one-sided prime ideal in non-commutative ring theory? Very basic question. And the standard definition is the way you usually do it in the literature. If you look at most of the papers, that you have an ideal either P, a left ideal P, and then you say that it is prime if whenever you have two ideals, left ideals ij contained in P, then one of them is contained in P. That's kind of the most natural guess. And he said, I want to do something different. He defined an ideal to be completely prime, a left ideal to be completely prime, if whenever A, B is in J, and J absorbs B from the right, we call that G is a left ideal. If it also absorbs B from the right, then it follows that A is in J or B is in J. That's the definition. And then he proceeds to write an entire thesis where he takes a bunch of theorems from commutative algebra, and he shows that they extend beautifully to non-commutative ring theory if you work with this odd definition. Once you get used to it, you see how natural it is. Well, we looked into it, and it turns out that this was exactly what we needed for our problem. We are going to define the radical implicitly, simply at the intersection of all completely prime left ideals containing our ideal J. Of course, in the commutative case, this is simply the usual definition of a prime ideal. So this definition of the radical is a certain generalization of a prime ideal from commutative of a radical from commutative algebra to non-commutative algebra. And now I can tell you what is I of z of j. It is the radical of j defined using these completely prime ideals. So you get something very natural, just like in the commutative case, except that it is not an explicit, only implicit description of the radical, but it still coincides with the commutative case, so this is nice to have. Okay, so I'd like to briefly sketch out the proof. So most of the standard proofs, the tricky, quick proofs of the Nullstellensatz don't work because of the problem, the same problem I showed you with the Rabinovich trick. So you need to do something a bit more conceptual, which is the Jacobson approach to the Nullstellensatz. So recall that a commutative domain is called a Jacobson domain or Jacobson ring if every prime ideal is an intersection of maximal ideals. And then there is the following result, a classical result, which is sometimes known as Nullstellensatz over arbitrary field, stating that any polynomial ring over a field in any number of variables is a Jacobson ring. Now, what we're doing is we're going to show that our ring of polynomials over quaternions satisfies a Jacobson-like property, namely every completely prime left ideal is in the intersection of maximal left ideals. And I will remark, and we will come back to this later, that we only prove it for the quaternions. In the commutative case, we know this is true over arbitrary fields. For the division rings, we only know it to be true over the quaternions. At least, so far, this is what we know. So how do you prove this technical claim? I need some auxiliary lemmas. So let us denote the center of the ring. so polynomials with real coefficients by R prime, we have the following going up lemma, stating that if you have a maximal left ideal in the center, then it lies beneath a maximal left ideal in the ring R. Another thing to note, which is true in arbitrary rings, is that every maximal left ideal is completely prime in this sense of Reyes. Finally, we have the so-called incomparability lemma, which states the following. Suppose you have two left ideals, P containing Q, such that the smaller one is completely prime. Then, if they agree on the center, if their contraction to the center is the same, then they are already the same ideal in the ring you start. Now, proving these lemmas, which I will not show, the first three is just standard exercises. The last one is surprisingly tricky. In the field case, it's very easy to prove it. You just go to the quotient rings and follows immediately. We were stuck on this for quite some time. And then one morning, my colleague Gil sent me a beautiful two-page proof of this lemma, which I will not show. But if anybody is interested to have a look at the paper, this lemma is the heart of the paper. And the only thing I want to mention about this lemma is that we only know how to prove it again over the quaternions. Gil's proof uses some explicit polynomial identities over the quaternions, which we don't have in arbitrary division rings. Okay, given these technical lemmas, I can tell you the proof of the Jacobson property. Take a completely prime left ideal in the ring, then its contraction to the center is a prime ideal just by definition in the usual sense. And since the center, just polynomials over the real numbers, is a Jacobson ring, then this P is an intersection of the maximal ideals contained in it. And by that going up lemma, every one of these maximal ideals lies beneath a maximal left ideal in the ring we started with. Which means that now, if you look at the intersection of all of these ideals, these M ideals lying over the smaller M's, you get a left ideal Q containing P, and just by set theory, it agrees with large P on the center, just like an exercise in set theory. Which means by the incomparability lemma, since we assume that this P is a completely prime left ideal, that these two ideals are the same, P and Q, which means that Q is an intersection of maximal left ideals, and hence P is an intersection of maximal left ideals. So this is the proof of the question.
Is it easy to show that the fifth point was before?
So fifth, I need to.
Okay, so the intersection with R prime is an intersection of maximal ideals, which are intersections of maximal ideals in R. Is it obvious that it follows that Q is an intersection?
Please say that again.
Sorry. So the second bullet point from the bottom. Is it easy to deduce that from the third bullet?
Okay, that it is a left ideal is immediate, contained in Q is immediate, and the intersection, yes, I think so, because the intersection of every one of these ideals with the center is, every M is small m. Maybe I should have chosen different letters so I can say it. Yeah, but okay, this is just an exercise in set. Okay, it's there's nothing going on here. Okay.
Oh, wait on. No, sorry.
Okay, and now I can just show you the proof of the Nullstellensatz. So by the weak version, we know that maximal left ideals correspond to points in the central affine space, which means that I of Z of J is the intersection of maximal left ideals containing J, simply by definition, which means that, and as you recall from the two slides before, every one of these maximal ideals is in particular a completely prime left ideal. Conversely, every completely prime left ideal is an intersection of maximal left ideals. This is the Jacobson property, which means that if you, again, just by set theory, if you intersect all completely prime left ideals containing J, it's the same as intersecting all maximal left ideals containing J, which is what we want. Which means that I of Z of J is the radical as we have defined. Okay, so this is a sketch of the proof. Of course, I've left out the heart of it, but this is what you get. Okay, but this already leads me to some follow-up questions. First of all, take an arbitrary division ring. So if anybody is looking for some paper to write, you can answer this question. So take an arbitrary division ring. Is the ring of polynomials over it a Jacobson ring in the sense defined before? So it's every completely prime left ideal and intersection of maximal left ideals. We do not know. If the answer is yes, that would be very desirable, because then it means that you can take the general Nullstellensatz over arbitrary fields and unify it with this result, and you get something that on the one hand gives the general Nullstellensatz, and on the other hand gives our result, which is specific to the quaternion. So this would be nice, that we don't know. The second question is, okay, so we have this explicit characterization. What about, we have this implicit characterization of I of Z of J, but it would be desirable to also have an explicit one. And we saw that the naive guess doesn't work. Maybe there is some other guess. So we didn't know how to do this, we didn't see it. And then just a few months ago, Aryapur, who's Masoud Aryapur, I don't know him personally, somewhere in Sweden, wrote a paper answering this question. So take a left ideal in this ring, then I of Z of J is the following. So it is all polynomials F such that, okay, it's going to be a bit complicated, for all quaternions A, there is a sufficiently high power such that AF to the M belongs to this left ideal, J plus J times 8F, JF square, and so on up until then. That's a characterization. It's not as nice as you would like, but this is simply the reality. It's more complicated, and this is what you get. And by the way he proves this, it's quite nice. So he went back to our problem with the Rabinovich trick that it doesn't work, and he forced it to work. So basically, if you recall, the problem was that we cannot translate the information back down. And what he did is said, okay, it doesn't work, but you had that substitution, that nice substitution formula I showed you from the second slide of the talk. Said, what happens if you try to use that formula and somehow force the information to trickle back down? And he did that, and if you follow through on what happens, you eventually end up with this more complicated description. So we didn't see that, he did, and that's very nice. I should mention that if you happen to start with a two-sided ideal, then you can immediately see that you simply get the usual definition of the radical, which is, again, nice to have. And again, the result holds specifically, his result holds specifically over the quaternions because he uses some of the results in our paper. So it's not clear what happens with arbitrary rings. So let me write some questions. So first of all, is the radical can be defined using his description in the case where D is an arbitrary division ring. So for fields, of course, this is true, but we don't know for arbitrary division rings. But more specifically, I would like to know, is it at least true for an algebraically closed division ring? So by an algebraically closed division ring, I mean any ring satisfying the Jacobson theorem. So a division ring for which the property holds that every polynomial with left coefficients has a zero. So what's the point that I'm getting at it? So the Nullstellensatz is only the starting point for algebraic geometry. And in any standard textbook in algebraic geometry, in any modern textbook, you start with the Nullstellensatz, and then you develop everything, but you don't do it just over the complex numbers, right? You do it over arbitrary algebraically closed fields. So what I'm trying to ask now is, okay, so moving forward, if we want to study geometry beyond just the Nullstellensatz, should we do it abstractly over algebraically closed division rings, or are we somehow forced to only consider the quaternion rings. And I should also mention the non-obvious fact that there are other examples of algebraically closed division rings that are not field, which are not the quaternions, so they are somewhat more difficult to come by than in the commutative case. First example is from Makar-Limanov in 1985. But even more generally, you can ask the following question. Take just an arbitrary ring. Do you have a description of this radical? The intersection of all prime left ideals containing it, we don't know, and we don't even have any guess. Okay. Next question. So, okay, we said that we could ask other questions moving forward in geometry, and there are many directions you can go for. Let me mention just one. So usually in algebraic geometry, you measure dimension using lengths of prime ideals, right? So if we kind of convince ourselves that this notion of completely prime left ideals is the right notion in our context, you can try to do the same. Then you can try to study the behavior of completely prime left ideals and ask, is it similar to the commutative case? And in particular, we're interested in their behavior under contraction. Is it well behaved? So let me make a concrete question. Just take a maximal completely prime left ideal, which is simply a maximal left ideal. Do they contract to maximal left ideals? So just to be very concrete, even in two variables, take a maximal left ideal in a ring of polynomials in two variables over a division ring. What happens if you intersect it with, if you contract it to one variable? Do you get a maximal left ideal? So we were wondering about this simply because we want to establish some dimension theory, and this is somehow the very first question you have to answer. And we didn't know how to answer it, and so we started to search the literature. Well, it turned out that this question was asked before us in the same paper of Amitsu and Small I told you about in the beginning. So in that paper, somehow the critical lemma for their proof is that if you have a maximal left ideal in such a ring, then if you intersect it with one variable, you get a non-zero ideal. And that's the critical lemma in their paper. Now, of course, if your division ring happens to be a field, then you get a non-zero prime ideal because maximal is prime. If you intersect the prime ideal with a prime ideal, you get a prime ideal. So you get a maximal, a prime ideal, which is non-zero, so it's maximal. So in the field case, the answer to this is, of course, yes. But for the division ring, Amitsu and Small, right, we remark that we are unable to show that maximal left ideals intersect in maximal or even semi-maximal left ideals. So semi-maximal simply means an intersection of finitely many maxima. So there are two questions here. If you contract maximal left ideals, do you get maximal left ideals, and if not, do you at least get semi-maximal left ideals? And then the second question was answered in 1979 by Small and Robson, and they have this result which simply states, if you read what's written here, division ring, okay, so they use right notation, but it's the same as that. If you have a semi-maximal right ideal, then the contraction is a semi-maximal right ideal. So if you have, in particular, if you have a maximal left ideal, then the contraction will be at least a semi-maximal left ideal. So they answered the second part of the question of Amitsu Small from the earlier paper, but not the first part. Then there was another paper by Resko, which gives some related results, but again mentions it remains unknown whether maximal right or left, doesn't matter, contract to maximal left ideals. And then I couldn't find anything else on this question up until 1995, where they have this paper of Rowan. And he writes something mysterious in this paper. He writes this question, this could fail when D is non-commutative, as shown recently by Amitsu and Small. So basically what he's writing, if you read the paragraph preceding, which I will not, he's writing that the answer to this question is negative, and that Amitsu and Small, the same people who asked the question originally, have recently showed it. Okay, so I've started to search the papers from around that time. I couldn't find any paper with the answer. And one interesting point is that Amitsu had died at September of 1994, which is the same month when Rowan submitted his paper for publication. Rowan is still with us, so I asked him, well, what did you mean here? And he says, I don't remember. It was 1995. And he suggested that I ask Lance Small, which is still with us. He's 80, but he's completely fine and active. So I've asked Small, and Small said that as far as he can remember, they never answered this question. So it's not clear what happened. There are two possibilities. One possibility is that they did answer it, and somehow, for some reason, they didn't publish it. Maybe it has to do with Amitsu's death, and simply Small had forgotten that they did this. The second option is that maybe something was lost in communication with Rowan at the time. I don't know. But anyway, I was very interested in this question because of the motivation the day before. And to make a long story short, I can give a counterexample to this question. So the answer to this Amitsu's question is negative. So I put my name on it, but reluctantly so, because I suspect that more likely it is that Amitsu and Small had already done this in 1995. And I will tell you the counterexample. It's very simple to define. You take a field K, and you take an automorphism of K, and then you look at the ring of Laurent power series, skew power series, over K twisted by sigma. So what does this mean? If for somebody who has not seen this object before, I know that you are very familiar with it. It's the usual, as an additive module, it's the usual ring of formal power series, but the product rule is twisted. So whenever you multiply the variable t by a constant a from the right, you write the constant to the left of the monomial, and you apply sigma. The left of the variable, and you apply sigma. And this gives you a well-defined ring. This was actually introduced by Hilbert for other motivations, which I will not get into. It's called the Hilbert twist. So you take this ring. It is well known that this is a division ring. And now you simply take an element in K that is not fixed by sigma, but is fixed by sigma squared. And then you consider the following left ideal: x plus t, generated by x plus t times x minus t, and y minus a. Okay? That's the ideal. And what I can show is that this is a maximal left ideal. This is actually not so obvious to see, and you actually need to do some work to do it. Because if you look at it kind of with your eyes, you might suspect that it is not maximal. It looks like it's contained right in x minus t, y minus a, but that happens to be the whole ring. So you need this thing. So you show that this is a maximal left ideal, and that intersection is the ideal generated by this polynomial, which is not a maximal left ideal. So this is the counterexample. However, I should mention that I was forced to use this kind of complicated ring, and you cannot write a counterexample with any underlying division ring that you'd like. And in particular, if you try to ask this question for the quaternion, then the answer is positive. Over the quaternions, it is true here that maximal left ideals contract to maximal left ideals, which is very good news, again, because we want to develop some dimension theory. So this is actually a consequence of our Nullstellensatz, and I will not show the details. Okay, so at least for this ring, maximal left ideals indeed are well behaved as we like, which brings me to the following question. Take a division ring D. We will say that D is an Amitsu small ring if the answer to the Amitsu small question is positive. So if maximal left ideals contract to maximal left ideals. And we will also say that a ring is a Nullstellensatz ring if maximal left ideals correspond to points in the central affine space. So if it satisfies the weak version of the Nullstellensatz. And I can show the following theorem, it's not difficult, that if you have an algebraically closed division ring, then it is a Nullstellensatz ring if and only if it is an Amitsu small ring, which is very nice. Which leads me to the question, are all algebraically closed division rings Nullstellensatz rings or equivalently Amitsu small rings? And again, the recurrent theme here is I want to know the answer to all of these non-commutative ring theory questions because I want to know, should I develop algebraic geometry over the quaternions specifically, or should I do it abstractly over algebraically closed division rings? And I still don't know the answer. So if anybody's interested, to help me out. More generally, you can ask, is there some nice generalization of the Amateur small rings simply in terms of the arithmetic of the ring itself without going to these polynomial rings? I don't know. I should mention, no, this is what I wanted to say about this. Yeah, I don't know, and I don't have a good guess. Okay, so there was one more part of the story I wanted to say, but I think it's been 50 minutes, right?
Well, 45 minutes to stop.
Ah, perfect. So let me tell you, I'll take 5 more minutes of your time to tell you one last part of the story. Again, a very recent one. So there was a paper a few months ago, or maybe it's a year now, by Gori, Zanfati, and Blacci, they're all Italians, and they looked at our paper and they said, we don't like what you're doing there. We don't like the fact that substitution is only defined in central affine points. We want to force the issue. So what does that mean? So recall, what was the problem? Why were we forced to limit our space? Because if you look at xy, which is the same as yn, how do you evaluate it at ij? That was the problem. And they said, well, there's no problem at all. Let's just fix an ordering and always decide to write x to the left of y. Problem disappears, and now substitution is defined everywhere. Seems reasonable. They didn't do it just to be petty. They did it because they have a bunch of papers dealing with the quaternionic analysis, and there they have substitution that is defined everywhere, and they were interested to know if they can put our work in the same framework as their work. So they have a good reason to ask it. Okay, so you can do this, and now you can perfectly evaluate x, y at ij, it's just k. And with this point of view, substitution is defined everywhere. But now this comes at a price, namely that the kernel of substitution map is, generally speaking, not even a left ideal, so this is not so nice. Nevertheless, given a left ideal, you can still try to ask the same question. So now, given a left ideal, we can associate to it 2 kinds of zero set. The one with central variable, so now with commuting coordinates, so now let me denote it by zc of j. So this is what we had before in our work. But you can also look at zeros without the restriction that the coordinates commute, and let's denote it by z of j. And then you can ask, what is I of z of j? Again, what happens if you try to go back and forth between algebra and geometry? Fair enough question. Now, a priori, it's not even clear that this should be a left ideal, but the point of their paper is that it is a left ideal. And in fact, it is the same ideal that you get if you only look at the zeros in the central affine space. So the point is you can try to look at a larger set of zeros, but you don't get any richer geometry. The main point of the paper is that what they try to do doesn't matter. But it's still a very nice theoretical property. So it's the same as our radical. And concretely, the point of the proof is the following. If you have a polynomial in 2 variables vanishing at the zeros with commuting coordinates, then it already vanishes at all the zeros. This is a very nice observation, which they have to do some work to prove. However, their proof is specific for 2 variables. And they conjectured that this should hold for any number of variables. And then we, again, myself and Gil alone, we were able to prove this. So this beautiful property holds for any number of variables. And after we had written a proof, they also written a different proof, maybe a few weeks later. Now let me ask a final question. Again, does this property hold if you replace the quaternions by a general algebraically closed division ring. And I should note that it does not hold if you look at an arbitrary division ring. There was a nice counterexample communicated to me by Adam Chapman. So there are many questions to study. Okay, so I think this is everything I wanted to say. Thank you very much.
Thank you. Are there any questions? So you say this is not some. This isn't satisfied for general. This property is not satisfied for general.
It is not.
It's very specific.
It is not, and it would be interesting to characterize the rings for which it works.
So all the questions you have so far are completed are mostly for quaternions, not for general.
Precisely. There are many questions that are remained open here, and this is very much work in progress. And a lot of people are, I mean, other than ourselves, there are now several groups of people who are somehow interested. Italian guys, and the Dariopour and Adam Chapman. A few people are trying to move forward with these questions, but I feel like there's a lot to do here, and if anybody wants to get into it, it's a very active kind of area now.
Right. Just remind how you find a completely prime left.
Yeah. Okay, I'll just write it.
Yeah.
So, let's say one more bit. Okay, maybe I will say. So, we say that P is completely prime. On the left idea, P is completely prime. If whenever A and P of course B from the right, it follows that either A or B belong to P. That's the definition.
Thank you. No need to think about
With your counterexample, the skew power series spring, is it like you know that you can never choose a case such that it's algebraically closed?
So in that example, K was the commutative field.
Yeah, but then K is going T, so that's a D.
So just a minute.
So
You start with then you have T sigma, and then what's your question about this?
Yeah, so that D can that ever be algebraically closed?
Okay, excellent question. So, okay, great question. I think the answer is no. I think the answer is no, but I'm not 100% sure. I need to work it out. Good question.
Right, yeah. So on the next slide, then you're right.
That would have answered.
This would be a
Yeah, I'm almost certain, but I don't have a very quick argument that comes to my mind. But just my feeling knowing this sort of object that there's no chance that this is right.
So, with these results in mind, would this mean you wanted to sort of define a kind of one could formulate a sort of non-competitive geometry of the do you know if you can carry any of the results, any of the results
So no, and I don't know, and I would like to. But so for example, my dream would be to develop some theory of singularity and prove some form of resolution of singularities or things like that. But as you saw, even the most basic notions here, the basic properties of the commutative case, become very difficult in the non-commutative case. So somehow my feeling that before you can really develop the geometry part, you have to first establish a bit more non-commutative ring theory the relevant things for this kind of theory before you can proceed. So this is what we're trying to do now. Then if this works out, then there would be many geometric questions to study.
Do you have an idea of what these sort of varieties would be? Would they be the sets corresponding to set C's or to the
So yeah, for the basic guess would be just you can start with if you say I'm only working over the quaternions, I'm not trying to do any schemes or anything like that, then you can just go a set of zeros and say this is my definition of a variety, or at least you can start with that.
Are there any other questions? Not, so let's thank Alan again. Would you, if you did, would you be interested in joining?
So I think I'm a bit exhausted. So yeah, but if you'd like to meet in maybe tomorrow or the next day about the problem we started to discuss,
I'll be around. I'll be around in tomorrow, maybe in the afternoon.
so we'll communicate. Thank you all.
Thank you all.